Good day, my angels. We are on to our second lesson of online learning. Sorry, no Star Wars introduction this week. But again, if for some reason you're unable to get to this, if you're working, if your situation is such that you just can't get to this or can't complete the homework, please contact me. Send me an email, let me know, and we will try and figure something out, because your physical and mental health are absolutely my most important priority. All right. Also, I'll send a solution key out on Wednesday, and I'll also send out an optional YouTube assignment on a Wednesday, and I'll try and remember to mention more of that at the end of the lesson. But let's begin. Last day we learned about momentum. We said that momentum was equal to mass times velocity, and it was measured in kilogram meters per second. Mass times velocity. Today, we're going to be talking about something called impulse, and I'm already going to start out by saying impulse is the same as change in momentum. An impulse is a change in momentum, and there's two ways to do that. You can either change the velocity, we call that an acceleration, or you can change the mass. We're not going to look at the changing mass situation very much, but an example of a changing mass situation would be if you're burning up some rocket fuel and the fuel mass of the rocket is decreasing. But impulse is a change in momentum. And I wrote here, we're going to start off with a proof. We want to prove that change in momentum equals mass times velocity change. I should point out, this topic that we're looking at today is both really tricky and really easy. So I'm just going to say to you, don't overcomplicate it right now. And my next lesson, I'm going to show you where we're going to use this. So we want to prove that change in momentum equals mass times velocity change. First, we're going to start out by saying change in anything is equal to final minus initial. Now, I put that on your formula sheet, I think on the front page in the top right corner. So if you want to, you can pause the video right now and double check to see where that is. Change in anything is final minus initial. And remember, the symbol for change in is a delta. So the symbol for change in is a delta. And I want to prove that the change in momentum equals mass times the change in velocity. So I'm going to put a question mark above the equal sign. I haven't proved it yet. Are they equal? Let's see if we can figure this out. Okay. Well, on the left-hand side, change in anything is final minus initial. So change in momentum would be the final momentum minus the initial momentum. You okay with that? That's how we've defined change in. And we also said that momentum was equal to mass times velocity. So I can write this as mass v final minus mass v initial. That's what the final momentum must be. That's what the initial momentum must be. So far, so good. This is the format that we'll often end up with. Final minus initial, final minus initial. But I want you to notice I can turn it into this format here because there's an m in both terms. I can factor out an m by GCF. And if I do that, I'll get m bracket v final minus v initial. And since final minus initial is change in, final minus initial is change in. This is m delta v. And I've proved what I wanted to. I started with this, and I ended here. So the change in momentum is equal to the mass times the change in velocity. And impulse is defined as the change in momentum. They're used interchangeably. If I ask you to find the change in momentum, I'm also asking you to find the impulse. If I'm asking you to find the impulse, I'm asking you to find the change in momentum. Impulse is change in momentum. You probably are going to want to commit this to memory, the idea that impulse is a change in momentum. Okay? Example 2 says, fill in the steps below to find the impulse equation. So we're going to start out with Newton's second law, F equals what, ma, and we're going to get the a by itself. That will give us a equals F over m. Acceleration is force divided by mass. We're also going to go to good old Vf equals Vi plus At, and we're going to get the a by itself there. That was the Vf would drop down like a domino, minus Vi all over T. And now we're going to say, look, if this equals acceleration and this equals acceleration, I can let them equal each other. F over m equals Vf minus Vi over T. Although instead of writing Vf minus Vi, since that's final minus initial, hey, that's also a change in. I'm going to write it like that. The last thing we're going to do is we're going to cross multiply to get rid of the fractions. I'm going to multiply the T up to there. I'm going to multiply the m up to there. And I'm going to get F times T equals m delta V. Now here's what this is saying. If you want to change the momentum of an object, if you want to apply an impulse, if you want to change the momentum of an object, if you want to apply an impulse, remember impulse is the same thing as change in momentum, you have to apply a force over a given time. You have to apply an unbalanced force over a given time. That's the only way to cause an object's momentum to change. I can also substitute the result from the beginning of the lesson. Where earlier we proved. Now I'm going to put the vectors in here. By the way, the direction of the force, that will be the same as the direction of the impulse. So if the force is north, the impulse, the change in momentum, will be north. And I substituted this in because we earlier did prove that m delta v was the same as change in momentum or impulse. This sounds really confusing. It's not. Here's what it means. This equation signifies that a force acting for a time will change the amount of motion that of a system, of an object. This equation is 3 equations in one. The way I wrote it on your formula sheet is something like this. I would have said F times T. I might have put a delta in front of the T because time is always a changing, equals m delta V equals impulse or momentum change. And remember that this is really mv final minus mv initial. I almost always break it up into this right away. So F net is the net force, what, ma. M is mass, delta T is the time, V initial, and V final. It's sort of 3 equations in one. Now, you may notice that I'm being way fussier with my vector notation. I'm paying way more attention to my vector notation than I have been for a while. And this is because in momentum questions, there are often changes in direction because momentum is used to analyze collisions and explosions. And often when you have a collision or an explosion, you have a change in direction. And so we're going to be using fairly meticulous vector analysis like we did way back when for velocity and acceleration. And what I mean by that is we'll let one way be positive and we'll let one way be negative, and we'll be consistent through the rest of the question. Okay? Let's look at one. Example 1. A .144 kilogram baseball is pitched due east at 38 meters per second. After it's hit by a bat, it moves horizontally due west at 55 meters per second. A says, what impulse did the bat deliver to the ball? Now remember, impulse is change in momentum. I have two ways I can calculate that. That's why I said this is sort of a 3-in-1 equation. I can use force times time, or I can use mv final minus mv initial. By the way, if you haven't paused the video, you should go look and see where I put this equation on your formula sheet. I think it's right next to the momentum equation. So which one of these am I going to use? Well, let's look and see what they gave me. I think I see a v initial. I think I see a v final. I don't see a force or a time anywhere in the question, so I'm going to use this one. mv final minus mv initial. But now we have to be very careful. Please notice I gave you directions. The ball came in going east, and the ball left going west. There is a change in direction. So I need to let one of these be positive and one of these be negative. It doesn't matter which one you pick, but you know what? Just for giggles, let's let east be positive. I'm going to put a plus sign above the word east, and I'm going to put a little positive in front of the 38. I'm going to put a negative in front of the word west, and I'll put a negative in front of the 55. And so now if I crunch this, the mass is 0.144. V final is negative 55 minus the mass is 0.144. V initial is positive 38. .144 times negative 55 plus 0.144 times positive 38, and I get an impulse magnitude of 2.448. I'll call that 2.45. The direction is negative, so I get negative 2.45. Impulse is measured in kilogram meters per second because it's a change in momentum. Momentum is measured in kilogram meters per second. If I wanted to give a direction, I would call this 2.45 kilogram meters per second at west, due west. I could have let west be positive and east be negative. If I did that, I would have gone 0.144 times positive 55. Wow, did I make a big mistake here? Sorry, folks. I hit a plus sign on my calculator. This number is totally wrong. You know what? I'll leave that on because I want to show you that I make dumb mistakes too. So let's try this again, Mr. Dueck. It's not plus. Impulse is change in momentum, which is the final momentum minus the initial momentum. That's better. 13.4, negative 13.4. That's the answer I should have got. Negative 13.4 kilogram meters per second, or 13.4 kilogram meters per second west. I'm sorry about that. But again, if I had let west be positive, I would have gone 0.144 times positive 55 minus 0.144 times negative 38, because east would be negative, and you'll notice I get the same magnitude. Oh, and I let west be positive, so I would translate this as west. So you can decide which way is going to be positive, which way is going to be negative. And what we've just found is the change in momentum on this baseball. What we've just found is the impulse of this baseball. Where does the impulse come from? Well, the bat applied an unbalanced force. Speaking of force, part C says, if the bat and the ball were in contact for 0.8 milliseconds. Okay, 0.80 milliseconds. That's 0.80 times 10 to the negative 3 seconds. I think that's what milli is. So that's going to be 0.0008 seconds, or as my calculator said, 8 times 10 to the negative 4 seconds. So there's my time value. It wants me to find the force. Now, we could find this as follows. We could go, don't write this down, we could go F equals ma. And we could find A by going Vf minus Vi over T. We would let one way be positive, one way be negative, and we have the mass, and we could just kind of crunch it there. And we could do that, but we can get there in one step. Because we know the impulse, we can write down the second version of the impulse equation. And the second version of the impulse equation says that impulse is also equal to force times the change in time. That's a vector symbol. Force times the change in time. How would I get the force by itself? Divide by t. Force, another way to calculate force, is impulse divided by time. Nerd trivia, this is actually Newton's second law. When he published it, he was not interested in F equals ma. He was much more interested in F equals impulse over time, but it simplifies to F equals ma. What's the impulse? Negative 13.392 all over, what's the time? 0.0008. So if I go negative 13.392 divided by 0.0008, I get a force of negative 16,700 newtons, or 16,700 newtons west. And what's nice about this is I was able to get the force in one line without having to bother finding the acceleration. And that's where the impulse equation shines. It's a great shortcut because it's an equation that combines inside of it final velocity, initial velocity, change in momentum, time, and force. You can survive without it okay, but it's really handy as a shortcut. D says, find the average acceleration. Okay. Again, I could go A equals Vf minus Vi all over T, but wait a minute. I just found the net force. I think I can go F equals what? Ma. I think I can go A equals F over M, and that's going to be negative 16,700 divided by the mass of 0.144. I'm going to use my answer button, of course, divided by 0.144, and I get an acceleration of 116,250, negative 116,250 meters per second squared, or if I wanted to make it a vector with a direction, meters per second squared at west. And again, this was nice. It let me get the acceleration in one line. I could have gone Vf minus Vi over T. And if you did it that way, I would give you full marks. But the impulse equation is a wonderful shortcut. Impulse is the change in momentum, and you can calculate it really in three ways. You can calculate it by going final momentum minus initial momentum, if you know that, or mv final minus mv initial, or force times time. Example 2a. What's the momentum of a 112 kilogram football player running due north with a speed of 3.6 meters per second? This is not asking for the change in momentum, the impulse. This is just asking for the momentum. So momentum is equal to mass times velocity. It's going to be equal to 112 times 3.6. 112 times 3.6. I get 403.2. I'll keep all the sig figs this time. The units would be kilogram meters per second. If you want me to add a direction, it looks like at north. B, what impulse must a tackler impart to the football player? Okay, impulse, another word for impulse is change in momentum. How will I figure that out? Well, again, there's three ways to find change in momentum or impulse. You can go final minus initial. You can go force times change in time. You can go mv final minus mv initial. You know what? I'm going to use this because the fact that we're bringing this person to a stop, I know their final momentum, it's 0. Because velocity would be 0. Minus, and I know their initial momentum, it's 403.2. I get an answer of negative 403.2 kilogram meters per second. Well, I called north positive, so what direction would this be? I guess this would be 403.2 kilogram meters per second south. If the tackle was completed in 0.8 seconds, now they gave me a time of 0.8 seconds, and they want the average force. Now, again, I could probably go A equals VF minus VI. You know what, though? What did I just find? I found the impulse. I'm going to use the impulse equation, and one of the versions of the impulse equation has a force and a time in it. So if I want to get the F by itself, F is impulse, just divide the T over. The impulse I have is 403.2. The time is 0.8. So if I go 403.2 divided by 0.8, I get 504 newtons. What direction? This would also be south, because the direction of the force and the direction of the impulse are going to be the same. Which makes sense. If a player is running north and I want to bring him to a stop, I have to apply a force south to bring him to a stop, or her to a stop. So I wrote here, although we solved this question using impulse, we really could have done it using Newton's second, F equals ma, and Vf equals Vi plus At. So why do we bother with momentum impulse at all? Well, the main reason is it's the best tool we have to analyze collision problems, which we'll get to in a couple of lessons. But there are a few questions, a few thought puzzles that can be answered using impulse. For example, if your folks are okay with it, you can try this experiment at home, but it might waste eggs, so maybe not. Let's suppose you drop 2 eggs from an identical height, h. One egg hits a concrete floor and breaks, splut. The second egg falls in a pail of water and survives. What's the main reason the second egg survives? Now, this is a deeper question than you realize. I'm going to do a little floor, water. Both of them have an initial velocity of 0. Both accelerate at negative 9.8 meters per second squared while they're in free fall. So both have the same V final, which really means both have the same impulse. They both go through the same change in momentum because their final velocity, right when they hit the ground, not after they hit the ground, but right as they hit the ground or the water, it's going to be the same. So why doesn't the egg break? Well, another way to calculate impulse is force times change in time. If I get the F by itself, if I can make the time of the collision last longer, if I divide by a bigger number, I'll get a smaller force. What the water does is it makes the impact last for a longer amount of time. Same impulse, same change in momentum, because both of them, their final velocity after hitting the ground is going to be 0. Their initial velocity when they hit the ground is going to be the same. Assuming they have the same mass, let's pretend they do, they have the same impulse, but I can make the time of impact last longer. And if I can make the time of impact last longer, if I divide the same impulse by a bigger number, I'll get a smaller answer. And in this case, the smaller answer is the force. It makes the force smaller. That's what crumple zones do in cars. All a crumple zone tries to do is lengthen the time of the collision. And again, because the collision time is so small, thousandths or hundredths of a second, even if you can double that, you can cut the force in half. So crumple zones are a very effective way to reduce the force in a car collision. Now, I don't want to write a big paragraph, so I'm going to say something like this. Floor, water. In the floor, when we hit the ground, it's a tiny time, and so that gives us a big force. The water, big time, tiny force. Same impulse, the same change in momentum. This is why Nerf objects don't hurt when they hit you. Although they have mass, and even though the change in momentum, the impulse, is the same as being hit with a hard object of the same mass, the sponge material lengthens the time of the collision. And because time got bigger, acceleration and force got smaller, doesn't hurt as much. Actually, the damage from change in momentum, from impulse, isn't caused by how much momentum is absorbed. It's caused by how fast change in momentum is absorbed. All of you have gone from 100 kilometers per hour to 0 kilometers per hour. Where has this occurred? Easy. When leaving the freeway and driving home. But the time it takes for you to go on to the on-ramp and you slow down a little bit, and then go on to the city road and you slow down a bit more, and then go on into your subdivision road where you slow down a bit more, and then go into your driveway where you slow down a bit more. We spread that time out over such a long period that you hardly even notice the force. So there, we make the time so big that the force is almost 0. Same impulse as in a car accident at 100 kilometers per hour to 0. The issue in a car accident on the freeway would be the time of impact is so small that the force your body absorbs is huge. Here's another way to think about the egg question. Why do they use bales of hay to line some racetracks, especially motorcycle racetracks? What's the advantage of being brought to a stop by a bale of hay instead of a brick wall? Well, In both situations, we have the same impulse. Our final velocity is going to be zero. Our initial velocity is whatever the racetrack is. But the bale of hay is able to lengthen the time of collision such that it makes the force of impact smaller, versus hitting a brick wall where the time of collision is so short that the force of impact has to be huge to cancel out the impulse, to bring your final momentum down to zero. In many sports that involve striking something, tennis, baseball, soccer, golf, etc., players are told to follow through when they come in contact with the ball. Why might this help the ball leave with greater velocity? Well, again, another way to think about impulse is this. Mass times change in velocity is force times change in time. Here's another way to write that 3-in-1 impulse equation. And if I want to get a bigger change in velocity, one of the things that I can do is I can increase the time that I'm applying the force. So as time increases, the change in velocity increases. In fact, if you play tennis, to do a drop shot, what you do is you yank back on the racket right when you make the impact to try and reduce the time as much as possible. Or if you play baseball, when you're bunting, you try and pull back right at impact to, again, make the time as small as possible so the change in velocity is much smaller. Example 6. What has more momentum? A 1,000 kilogram car moving at 100 kilometers per hour, or a 2,000 kilogram truck moving at 50 kilometers per hour? Now, I don't like the units. This is kilometers per hour. This is kilometers per hour. And if I really, really wanted to dive into this, I would convert this to meters per second. But you know what? I think they're the same, because if I just go mass times velocity, even with the wrong units, I get the same answer, I think. Let's double check. If I go 1,000 times 100, and if I go 2,000 times 50, yep, twice as fast, half the speed, that truck will have the same momentum as a car going, going half the mass, but twice the speed. So here, they are the same. Does a moving object have momentum? Well, momentum is mass times velocity. So does a moving object have mass and velocity? Yes. Turn the page. Does the moving object have impulse? Well, impulse is a change in momentum. It's mass times a change in velocity. So does a moving object have impulse? Not if it's going at a constant velocity. It has momentum, but no changing momentum. By the way, if you're at a constant velocity, that also means the net force on you is zero. Well, of course it is, because if there was an unbalanced force, another way to calculate impulse is force times time. When you jump from your lab table to the ground, why do you bend your knees as you land? You figure this out when you're 3 or 4 years old on playgrounds. When you start jumping off of stuff, you learn that when you hit the ground, you bend your knees. Why? What does this do? Well, this is the same as the egg in water. Bending your knees increases time, lowering force. We're stuck with the same impulse because when you jump off of something, when you land on the ground, after you hit the ground, your final velocity is going to be zero. Your initial velocity depends on how high you jumped from, but you're stuck with that change in momentum. But if you bend your knees or even tuck and roll, if you're jumping from a really high height, you're increasing the time of impact, decreasing the force. So again, impulse change in momentum, is equal to the force times the change in time, or impulse, change in momentum, is equal to the mass times the change in velocity. And since change in anything is final minus initial, I usually write it that way, which also means that force times the change in time is equal to mass times the change in velocity. This one is going to be really handy next lesson as a lovely shortcut, because look at what it contains. Force, time, mass, final velocity, and initial velocity. It's really what we would get if we combined several equations into one. It's a lovely shortcut. Also, another unit for momentum or impulse would be Newton seconds. If you're finding an impulse, you can tell me the answer is kilogram meters per second. I'm fine with that. You can tell me the answer is in Newton seconds. I'm fine with that. I'll take both. I suspect right now a lot of you are kind of confused. Relax, work your way through the homework, don't panic. I find on the third lesson it becomes much, much, much clearer. So what's your homework? It's going to be every question. So number 1, number 2, 3, 4, 5, 6, 7. Again, you can do them on a separate piece of paper if you want, or you can simply, however you want to share the answers with me. It's fine. I'm good with that. A little reminder, I'll send out a solution key on Wednesday. Excuse me. I'll also make a YouTube video explaining how to do every question. I'll also send out another optional Wednesday YouTube assignment. This will have 4 different YouTube channels. If you didn't catch that last week, by the way, if you have any missing assignments, you can do them, and if you can get them to me, I'll give you full marks. Or if you want to, on Wednesday, I sent out 4 YouTube channels. Pick one of them. Watch any video from that YouTube channel. They're science-based YouTube channels. Email me the link and email me what you learned from the video and which assignment you would like me to replace. So you'll have 4 new YouTube channels this upcoming Wednesday. Okay? Again, my angels, be safe. And again, if you have any questions or concerns, or if you need help with the homework and you want to arrange a Zoom meeting, I can do one-on-one Zoom meetings or 1-on-2, 1-on-3, or group ones if you want. I'm trying to free that up for other teachers that don't know how to create screencasts and post them on YouTube. So that's why I haven't been doing any live sessions myself. But if you want some one-on-one help, I'm free evenings, I'm free during the day. Let me know and we can set up a time. Take care, my angels.